So, good afternoon. Again, here's the title. I'll talk today about a collaboration with Vrnjačka from and what was at the time the Adelaide group in South Australia about a correction to this tadpole cancellation conditions for relating D3 brain charges to the fluxes which are around in type 2B string theory. Okay, so first let me explain what this usual one is. So the usual tadpole cancellation condition for the three-form fluxes in 2B you can derive just from the classical supergravity. In fact, it's not just that you can derive it from the classical supergravity, but in fact it's not true in the quantum theory. I'll argue today that there'll be corrections in the quantum theory. So really the most you can do is derive it from the classical supergravity theory. In the classical supergravity theory, the structure comes from the fact that there is a kind of unusual gauge transformation. The gauge transformations in type 2 supergravities look kind of like the gauge transformation just in QED, but you have this extra term, which is related to H, the Novo's free form. So you have this kind of more complicated than usual gauge invariance. This is what's going to give all the structures. Because you have this extra term in the gauge symmetries for the Ramon-Ramon connections in type 2 supergravities, that means there are two different types of field strengths you can make. So in QED, there's only one kind of field strength. You just take the the connection. Here we've got two kinds. The first thing we can do is we can construct something which is gauge invariant, which is D of the connection plus something which compensates for the extra term. So this thing will be gauge invariant, but it's not going to be closed. It's not D of something, which is the usual argument that it's closed. Also, we can just take D of the connection. If we take D of the connection, we get something which is closed, but it's not going to be gauge invariant. And this is the thing which in the quantum theory is going to get quantized. So in supergravity theories, we have these two different notions of field strength. Again, we can define charges using the Bianchi identity, and which thing you take D of to define your charge is a matter of convention. But the convention that I'm going to use is I'm going to take D of this thing, the closed thing, and define this to be charge. And so I could write it this way if I want. With this definition of charge, I can now integrate this equation over any compact set cell. And the integral of E7 minus P brain charge density over any 6 cycles is going to be the net charge, the intersection number of the D brains per minute cycle. On the other hand, I can integrate over here. Integrating this, I just write it itself, but here I'm interpreting these things as cohomology classes. This F was gauge invariant, so when I integrate this over a D6 cycle, it's D of something, which is globally defined. And so by Stokes' theorem, the integral of this term vanishes. So the integral of df over a 6 cycle is just the integral of f over its boundary, which is 0 because it doesn't have any boundary. And so in the end, we find the usual tadpole cancellation condition that the D brain charge is just given by the wedge product of these two things. Okay. So that's the classical case. I want to consider the quantum case. By quantum case, I don't mean in the previous talk's quantum case, not that I'm going to make all the operators observables non-commutative. In this case, all that I mean by the quantum case is that there's going to be a partition function for the strings and the brains in this theory, and I'm going to impose that these partition functions are well-defined, and by imposing that, we get some quantization conditions. And the direct quantization conditions are just these, that the integrals of the Ramon-Ramon fluxes have to be integral. Okay, so in this case, there are two different kinds of effects. The first kind of effect is that you have, before there was a continuum of Ramon-Ramon fields, you could have any integral, and now we restrict to certain values of the ones that are integral. The second effect is that if we just if we don't care at all about what the connections are, and we ignore Ramon-Ramon field strengths, which are D of connections which don't satisfy the quantization condition, then we're going to get some new values of the fluxes, which we would have said were trivial in the classical theory. These are what are called the discrete torsion fluxes. And so these are the fluxes which, for example, are sourced by torsion brains. Torsion brains are brains such that, for example, if you have n different brains, they can come together and decay. These brains are always unstable, as I'll show in the classical theory. But in the quantum theory, they're very real without these Z-inversion brains. Okay, mathematically, this just means we go from the real cohomology to the integral cohomology. And so any RK, which used to classify where K is the number of cycles, the original cohomology is going to question is going to be, we take the old tadpole cancellation condition, which applied to this RK. It's easy to figure out what it does to this DK, but now there are all these extra fluxes around in the quantum theory. And so you can ask, what's the condition on these extra fluxes? And so that's the question that I'll answer for. Okay, so let me give you an example of how this direct quantization condition can give you extra brains. So, before I was talking the language of fluxes, but I can equivalently talk about the branes which source them. So for example, if I'm doing PEP-QE on RP3 across Minkowski space, RP3 has this cohomology, the 0th and 3rd cohomologies are Z, the other cohomologies are 0. And so classically that means they're basically two transfer branes. They can either wrap the whole RP3 or they can be points in the RP3. You might remember that RP3 is a group manifold. SO3, it's got a non-trivial one cycle in it, such that if you go around that non-trivial one cycle twice, it's deformable to be identity. In the classical theory, I'll show momentarily that a brane wrapped around this non-trivial one cycle is actually unstable. So the reason in the classical theory that a brane wrapped around this non-trivial one cycle is unstable is that a brane with any charge q can just split into two branes of charge q over 2. These two branes of charge q over 2 can go into a brane which wraps twice around the cycle. But going around the cycle twice is trivial. You can deform that away enough. And so by this decay process, any brane in the classical theory which tried to wrap around the one cycle in this RP3 can decay. And correspondingly, it didn't show up yet.
These branes come with bundles over again.
Sure.
So, and that modifies your statement that we should think of them of their charges as taking values in the cohomology.
So the bundles are going to give you the lower D brane charges. The lower D branes may represent non-trivial elements in the homology. In this case, they won't, because there aren't any classes on the one side, because there are no chain classes which are degree 1. In general, I could have considered a two-cycle in a different example, which would have had some non-trivial chain classes. Then there would be lower D brane charges. So this D brane charge here, it would be topologically trivial. However, after the decay, the D brane charge, which corresponding to the field configuration, would still be around. This would be a lower D brane charge, and this lower D brane charge would have corresponded to one of the original homology classes. And so you don't really get anything new that way. I mean, equivalently, you can take whatever your non-trivial topology is of this H field, and you can just take those branes and remove them from the brane which they're embedded in. And you can see that they have to correspond to these homology classes.
So you're saying that this doesn't modify your statement?
No, you don't get anything new by dissolving branes inside these branes. I mean, if you dissolve other branes inside these branes, those other branes still have the original charges, so you haven't really done anything as far as changing the number of charges. So you just move them around in space and maybe use them. But you don't get any new charges at all. I mean, you don't get any charges in addition to just the homology of your total space. Right? Remember, like the D1, D5 picture. We have a D1 brane you can dissolve inside a D5. That D1 will only be non-trivial if it wraps a non-trivial cycle. There's the instanton number is always valued in the original, in the actual homology of things.
Are we supposed to think of gate theory instead of homology?
In the classical case, no. No, in the classical case, we should be thinking about cohomology. Actually, I'm going to argue that K-theory gives you the wrong answer here. But you'll see how it is that K-theory comes into this picture soon. We're going to talk about this. Okay. So let me talk about the quantum case first in this example of just RP3 cross RP. Cross Minkowski space. So in the quantum case, there's an extra cohomology group around the Z2. If we're classifying branes instead of fluxes, we should actually think about the homology. So now it's H1 and Z2. And so this is that cycle that you can go around twice, and this would be non-trivial. And in the quantum case, you can wrap a brane around the cycle. And this brane will be non-trivial. And the reason is the decay I described before, where the brane of charge Q splits into two branes of charge Q over 2, you can't do in the quantum case if Q is odd, because there's a direct quantization condition. You can't just divide any charge by 2. Charges have to be in. And so if you have charge 1, then this decay doesn't happen. And so these branes are really Z2 charged, and they're there in the quantum theory. So the quantum theory has got more branes than classical theory. And quantum gravity that will cancellation condition should tell you just what branes there will be, or what fluxes there will be on that side. Okay, so here is our claim for what the answer is. The claim is that in the classical case, the D brane charge was just G3 wedge H. Here I'm using language of integral wedges with cups. It's just a general integral homology. So in the quantum case, we say there'll be three kinds of corrections. There's G3 cupped with itself, H cupped with itself, and some P, which is unknown but is independent of G3 and H. So you calculate whatever G3 and H is easy, and then it'll work for the other ones. If the K-theory classification was correct, then we would have only found this term and this term, and we wouldn't have found this, or we wouldn't have found either of those. So the K-theory classification we'll see is incorrect here. In fact, the answer you get from K-theory isn't even S-duality covariant. If you switch H and G3, it changes. And so the K-theory classifications could never have given you the right answer. But we'll see where it is that K-theory goes wrong momentarily. Okay. So how is it that taking cup products of three classes with themselves, wedge products of three classes with themselves, of course, vanish because it's anti-symmetric. With a cup product, that isn't clear because x3 cup x3 is negative itself because the cup is anti-symmetric, but that just means that x3 is Z2 value. If you're negative itself and your Z2 value, you could be 0 or 1. Okay. So the tool that I'll use to derive this claim up above is the free loop anomaly. And I'll review for you now what the free loop anomaly is. First, I'll review what you've already heard about in recently in questions, which is the way lower dimensional brain charges dissolve inside of brains work. So if you have a DP brain, there's one sector in its action, which has to use West amino terms. And basically it looks like this. You've got the charge to the brain itself, then you've got the exponential of the B field, the NS2 form, plus the field strength of its U1 gauge field, and then you've got a sum of all of the different hormonal connections. And this you can expand out this way. This term here, the F Cp minus 1, has the interpretation of lower dimensional D brain charge. So dp minus 2 brain charge in this case. Because if the integral of F is some number, A, and if the charge of the dp brain is 1, then you can do the integral of the F, and you'll be left with just the integral of Cp minus 1 times A, and this is just the action for a dp minus 2 brain of charge A. And so dp brains can carry dp minus 2 brain charge if they have magnetic flux. This is the F. Alright, so that's the F term. You could ask about the BCP minus 1 term. Why isn't that giving you dp minus 2 brain charge? The key is, well, one reason that it would worry you if it did give you dp minus 2 brain charge is that it's not quantized, because the B field isn't quantized. So it would worry that doesn't mean it's not there. However, there's a paper by Waddy Taylor a couple of years ago where he showed that the contribution to the dp minus 2 brain charge of this piece times dp minus 1 is always canceled by another contribution from the bulk. So if you have a brain which wraps some cycle, you can think of the interior of the cycle as long as there's no non-trivial topology, and we'll see how that comes in momentarily, and the contribution of the charge there which exactly cancels this one. And so the lower brain charge just comes from this term, it's F Cp minus 1. Okay, so you might ask what happens if there are two different ways that you could do this argument by Waddy Taylor. If there are two different interiors. For example, if you have a 3-sphere with H flux, then you might wonder what the interior of any given brain which wraps a 2-sphere inside the 3-sphere is, because you can close it one way or you can also close it the other way. And if there's non-trivial H flux, you would get a different answer for the integral of B, depending on the two ways. And so you might wonder that, think that there'll be some kind of problem when you have non-trivial H flux. And I'll show you momentarily that indeed you do have a problem when there's non-trivial H flux. But a problem which is solvable. So if you have a 3-cycle with non-trivial H flux, so the integral of H over that cycle is non-zero. Remember that in the effective action of any D brain, the quantity B plus F is gauge invariant, where B is the NS2 forming it and F is the world volume field strength. In particular, this means that D of it, by Stokes' theorem, I can argue is 0. So D of B plus F is just H plus DF. By Stokes' theorem, I can say that's just the integral of D plus F over the boundary. There is no boundary because the factor is 0. So H is equal to minus DF on the world volume of any D brain. DF is the charge of the magnetic monopoles. So magnetic monopoles on a DP brain are just DP minus 2 brains which end on it. So the number of DP minus 2 brains which end on any DP brain is just equal to the amount of H flux that the DP brane wraps. So DP branes can wrap H flux, that's okay, but if a DP brane does wrap H flux, it needs to have DP minus 2 branes which end them. This is a classical version of the free-wood anomaly. And you can make a similar argument using S duality for NS5 branes. So an NS5 brane, which is wrapping G3 flux, is going to have D3 branes which are ending up. This is part of where K theory is going to fail. It turns out that K theory misses these S dual anomalies. Okay, so that was what I was just talking about, the classical version of the free-wood anomaly. So what about the full quantum case? In the quantum case, we augment it with the fact that this partition function for the fundamental string has to be well-defined. So this is the argument of free and wood. The partition function for a fundamental string, they show it has this factor, the exponential of b plus f plus w2. This factor has got to be well-defined, and so that means that d of b plus f plus w2 needs to be integral. So we've just seen that the integral part of it vanishes, and so really d of b plus f plus w2 has to be 0. So what is the integral of d of b plus f plus w2? D of w2 gives w3, d of b gives h, and d of f, we just saw is magnetic monopole charge, which is the dp minus 2 brane charge. And so the dp minus 2 brane charge classically was just minus the integral of h, but mechanically there's a correction, which is w3.
Can you just remind us what is W2 again?
W2 is the second C4 class of the normal bundle of the D brane. W3 is its third C4 class. That's okay. Other questions? Okay. So the free-wood anomaly shows you that you can have a DP brane wrapped around a cycle with non-trivial H flux plus third C4 class of the normal bundle, but this DP brane has to have DP minus 2 brane insertions. Okay, so this is all that I need to demonstrate the claim. So the strategy for the claim is, let's start with the space-time, which is r times some m naught. In fact, I don't really need this r, but it makes it a little easier to draw the pictures. And I'll start with all of the free-form fluxes turned off, and I want to turn on the free-form fluxes and see what kind of D3 brane charge I get. Because remember, the condition I want to prove is the relation between the D3 brane charge and the fluxes. So if I start with the D3 brane charge, the flux is turned off, and I say there's some number of D3 branes, which I'll just call P, then I can turn the fluxes on one at a time and see how the D3 brane charge changes as I do this. So the way I'll turn these fluxes on is I can turn on H flux by wrapping an NS5 brane around some cycle at a fixed value, a fixed point on this arc. Then I can turn the G3 flux on by inserting a D5 brane at some fixed value on arc, where the D5 is dual to whatever it is the free-form flux is that I want to turn on. So then I've turned on whatever flux I wanted, but this NS5 brane and D5 brane will have free-wood anomalies. These free-wood anomalies will be cancelled with D3 brane insertions, and so the D3 brane charge will change. And in fact, you can just compute it using the free-wood anomalies and less transparency, and you find that at the end, you still have your original units of D3 brane charge, plus you get this D3 brane charge from the NS5 brane, plus this from the D5 brane, and so in total, you have this plus this D3 brane charge. And that was just the right-hand side of my claim. So the D3 brane charge, so with an arbitrary G3 and H flux, you get this D3 brane charge, which is the correction to the tadpole cancellation condition. And in the calculation, I use the fact that I can do this integral of the third C4 class, and it just gives these square terms here using a simple property of the SEENET squares. Okay, so that's it. That demonstrates the claim. Sometimes you might have seen this I star in the transparency before, but more generally, sometimes these DP branes have anomalies which can't be cancelled by including DP minus 2 branes. Sometimes you need DP minus 4 branes. And in that case, you get more complicated anomalies, which won't be important for calculating the D3 brane charge, but would have been important if I wanted to work out a generalization that's for D1 brane charge. So for that, I'll need a more complicated free-wood anomaly where you have D5 branes, which might have D1 branes ending on it. And there is no known formula for how to compute the number of D1 branes that need to end on the D5 brane to cancel the free-wood anomaly when this turns out to be non-trivial. There are conjectures for what various terms are. It's known that it's non-trivial, but nobody knows quite what it is. So that's one generalization you can try to do, is find the condition for lower D brane charges. Another generalization you might be interested in, that seems like everyone has for when I talk about this, is generalization generalizing the case where you've got oriented folds around or where there are orbital folds around with vertical fixtures. The analysis above doesn't apply to either of those cases. That would be very nice because, for example, if you're trying to do phenomenology and you've got a clavia of 3 fold around, remember these corrections. They're G3, cup G3, or H cup H are the Z2 value. But in a clavia, H6 is always equal to Z, and so there's no Z2 around. And so this will never come into play. These corrections will always be trivial in the case of clavia 3 fold, although there are certainly plenty of applications where they're not trivial. But once you put oriented folds in, then this could all change and it could become relevant. Okay.
Are there questions?
Now, if you wanted to generalize this to oriented, for example, you wanted to derive the tadpole cancellation condition from the ambit.
Yes.
How would you incorporate this modification?
Good, so I wouldn't be starting out with the usual homology because the charges in an oriented fold aren't classified by the homology of the space-time because you have to do the Z2 identification. You consider things which are even or odd under this, depending on the fluxes. And so I have to replace this homology with the Z2 twisted homology, which applies to oriented folds. This is reviewed, for example, in say for Anani and Bull talk about the Z2 homology groups around oriented folds. So I have to use a different kind of classification for the fluxes. And then I also need to find the Fried-Witt anomaly in that case. The paper by Fried-Witt only applied to type 2 without any oriented folds. So this equation for the string partition function, which was very crucial there, this E to the I, B plus F plus W2. Nobody knows the analog of that when there are oriented folds around. And so that's really the main obstruction because although the derivation is simple from that point, to derive that formula to define this phase was a very difficult theory calculation by Fried-Witt. Probably it would be difficult for me anyway. But that's the main obstruction.
Are there other questions?